Let's continue with section 1.2, domain and range. In functions and function notation, we were introduced to concepts of domain and range. In this section, we will practice determining domains and ranges for specific functions. We can write the domain and range in interval notation, which uses values within brackets to describe a set of numbers. In interval notation, we use brackets and parentheses. Here's a chart to showcase all possible forms of writing domain and range in interval notation. So I don't know if there's a moment where you would like to pause the video and see each segment in detail, but generally parentheses are for when it's not included or when it's just less than or greater than, right? So if I have less than or greater than, then I'm going to use the parentheses. If I have less than or less than or equal to or greater than or equal to. If I have that equal to, that means inclusion. So there you would want a bracket. And remember, infinities always use a parentheses. So here we can represent an equality in interval notation. Notice that interval notation is helpful because it just lets us find a stopping point, and from there we can go ahead and continue. How to find the domain. We ask ourselves, what can X be? Here are some restrictions to consider. The first is there a radical? If so, set the radical to greater or equal to 0. I'm sorry, the radicand, which is your argument in a radical. If there is a fraction, then set the denominator to not equal to 0. This will help you determine what your answer should be. All right, let's do this example. Find the domain of the function. A, f of x equals x squared minus 1. To find the domain, we have to ask ourselves, what can x be? Is there some type of restriction to what x may be? Well, here we see, if we consider the x that's being squared, there's no limitations. A positive can be squared, 0 can be squared, a negative can be squared, any number can be squared. So for this one, there's no type of restriction, so our answer is all real numbers. And if we wish to write an interval notation, it would be infinity or negative infinity to infinity. Let's take a look at B. We have f of x equals x plus 1 over 2 minus x. All right, here we do have a problem. It can never equal 0 in the bottom, right? Because that would give us an undefined statement. So we want to find out when it's not equal to 0. So we take 2 minus x and we solve for when it's not equal to 0. All right, we can go ahead and just move the x. So plus x on both sides. We're left with 2 cannot equal x. We like to see the x first. So we say x cannot equal 2. And that is our domain. Now, if we write this in interval notation, to do so, I like to first draw a number line so I can see what we're working with. And what we're saying is it can be any number but not 2. So 2 is excluded, but it can be any number to the negative side, any number on the positive side. So our answer in interval notation would be negative infinity, and then I would have to stop at 2. Infinities always have a parenthesis, and this 2, because it's not included, has a parenthesis. We have a union or break, and then 2 to infinity. And that's our domain. Let's take a look at C. All right, here I have to consider what can x be, what can give us a problem. So we have a radical. I know I can take the square root of 0. That's just 0. I can take the square root of a positive number. I can take the square root of a positive number that's not a perfect square. but I cannot take the square root of a negative number. That would give us an I, and we know that that's not in our real number system, so we'll hold off for that. So that would be our only problem. So we want to find numbers that would give us something greater or equal to 0, since 0 is allowed. So we take our radicand, 5 plus 2x, we want to find out when it's greater or equal to 0. So you subtract 5, and we're left with 2x must be greater or equal to negative 5. Divide by 2. Yeah, x is greater or equal to negative 5 over 2. And that's our answer. That's our domain. And we want to write in interval notation. So let's graph it. So I have negative 5 over 2, and I want all numbers that are bigger than that, so to the positive side. And that number is included, so I use a closed circle. So if I wish to write this in interval notation, that would be negative 5 over 2 to positive infinity. Infinity is always use parentheses because we have an equal to, and because we have that makes us use a closed circle, we use a bracket. Set builder notation. Set builder notation is a method of specifying a set of elements that satisfy a certain condition. It takes the form x such that, and then statement about x, which reads as the set of x such that the statement about x is true. So in a general sense, what you want to write is your curly bracket, the variable you're working with, that line, and then close your statement. There you include whatever inequality your answer has. And you read it as x such that, and then whatever else you have. Interval notation is a way of describing sets that include real numbers between a lower limit that may or may not be included and upper limit that may not be included, that may or may not be included. The input values are listed between brackets or parentheses. A square bracket indicates inclusion in the set, and parentheses indicate exclusion of the set. All right, let's do an example. Describe the intervals using inequality notation, set builder, and interval. All right, so let's write this down. Let's take a look at this first part. So do you see how we have 1 and 3 sandwiched between our answers? The way we write this is we write a 1 and then a 3 and an x in the middle, and we're always going to use less thans. When we have an enclosed area, it's always less thans. Because we have closed circles, you see how the circles are closed? This means we have equal to, so we have less than or equal to for both. That is our inequality for that first part. And our unit circle, in our number line, we also have this other graph. So this is saying that x, and we start with 5, and then it goes on forever to the positive side. So x is greater than or equal to 5. Not equal to. Do you see how this is an open circle? This means that it's strictly greater than, no equal to. Okay, now we have our two inequalities for our statements in the number line. In inequality form, we have just as we developed above. Set builder, we have the same thing, but we introduce the curly bracket x and that such that bar and that closed curly bracket. Interval notation, I think you appreciate a lot more here. Here we see our interval notation. We see we start with 1, we end with 3, they're included, we put brackets, and then we continue on to 5 to infinity. That's our interval notation. That U is called a union. And that just means that the collection of it is part of our answer, or the sum of it. It means everything that's listed is part of our answer. So we can say maybe a collection of. Finding domain and range from graphs. Another way to identify the domain and range of functions is by using graphs. Because the domain refers to the set of all possible input values, the domain of a graph consists of all the input values shown on the x-axis. The range is a set of all possible output values which are shown on the y-axis. So our domain is whatever x can be. So you want to look at your graph and you want to connect it back to what the x value is. If it goes on forever, it'll have some arrow, or if it stops, you need to know exactly where that point stops, like here, x comma y. That would be a stopping point, so we'll look at the x for the domain. Here it continues on forever, so we would assume our domain will go on forever too. Because it's to the positive side, there will be some positive infinity. Now let's talk about range. For range, same idea, but kind of backwards. We want to look at how far up and down our graph goes. So I want to look at my y's. So here I will have a stopping point, and I want to look at my y, because that would be indicated what the stopping point is. Or if it goes on to infinity, then my y will continue on to, well, here I have my negatives, so to negative infinity. So for domain, you look left to right. For range, you look up and down. So domain, you look left and right. For range, you look up and down. Graphing piecewise defined functions. Sometimes we come across a function that requires more than one formula in order to obtain the given output. A piecewise function is a function in which more than one formula is used to define an output over different pieces of the domain. Let's take a look at the example. So here we have three different graphs. We have x squared, which is a parabola. We have y equals 3, which is a horizontal line at 3. And we have x, which is y equals x. So it's just a line. We have three different graphs. And within each of these three different graphs, we have restrictions. So for the parabola, my x values, I only want them starting at 1 to the negative side. So x is less than or equal to 1. For my 3, I only want it between 1 and 2. And for my line x, I only want it when x is greater than 2. So starting in 2 and bigger values for x. Let's take a look at each one separately. So for my first one, which is x squared, when x is less than or equal to 1, we see we have a parabola, and we start at 1, and we see that the numbers from there are smaller, right? We've picked smaller numbers to work with. And it continues on forever. My domain doesn't have another restriction. Next, for my 3, have 3 if 1 is less than x less than or equal to 2. That's telling me that I want a horizontal line at 3, but I want it only between 1 and 2. Notice that 2 has that equal to, so we have a closed circle, and 1 is only less than, no equal to, so we use open circle. Lastly, we have y equals x, or just x, and x has to be greater than 2. So we have our graph at x, but we only want it starting from 2 and on. But notice it has an open circle because there's no equal to. You see how there's no equal to on it? So we use an open circle, and we want x greater than 2. It doesn't tell us where it stops, so we write an arrow. Now we have all three of them graph separately. We can put them together, and that is our answer. That is our answer to our piecewise function. Together, they make up our collection of 3 functions with the given domain restrictions. Sometimes when I'm a bit confused, I graph a function as is, and then I look at my domain and I erase whatever is not part of my answer. All right, that's all for 1.2. We'll continue with 1.3. Thank you.